All right. So first, I want to thank Mr. Michael Hafey for the recognition and award for the DSP, and I want to congratulate the other winners as well. So my name is Alex Luteski. I work on the standardization team at the Detroit Arsenal in Warren, Michigan. Let's go to the next slide. So just a brief background here. The U.S. Army still uses cadmium and hexavalent and chromium plated steel fasteners on its programs. When this project started, we're supporting PEO GCS, Program Executive Office Ground Combat Systems. And the basis for this project was the automotive industry. Back in the 1990s, the automotive industry moved away from cadmium and hexavalent chromium. They updated their specs accordingly. That did not happen with the military. So for the automotive industry, the common replacement was zinc nickel with hex chrome free passivation. As a result, what the Army experienced, where the Army programs were in a situation where the newest produced vehicle systems launch with zinc nickel fasteners, but in sustainment, they can be procured. What happens is then the PM, the program manager, has to walk back to using zinc with trivalent, which is slightly better than zinc with hexavalent chromium, but it's still not a perfect solution. Usually that was an alternative. So the reason they're using zinc with trivalent is because it is more commonly available with part suppliers and the manufacturing base. So on this slide right here, you have an Army Acquisition Executive Memo, AA memo from 2022, which, as you can see here, the title is Elimination of Hexavalent Chromium in Army Acquisition and Sustainment of Weapon Systems. So this memo right here listed elimination dates for a lot of things you see here, paint primers, surface treatments, and so forth. We highlighted C, coatings, because that's something we were working on. So this memo kind of led to some urgency, and it led to some creation of commercial item descriptions, which we'll talk about later. And I know Mr. Hafey also inquired about that, and we have a specific slide for that later on. But this memo kind of led to some urgency in updating the specs. So that's kind of what dictated the Army to go that way. So before we get to some testing data, we wanted to kind of talk briefly about cadmium and chromium. So as you can see here, cadmium is a carcinogen, and by being a carcinogen, it is hazardous to human health and also to the ecosystems. You can also see here that long-term exposure to cadmium can result in cough, anemia, kidney failure, and also cancer. We've actually worked with a couple of folks who know friends who work for plating shops, and they have personal stories to tell where they have friends who only now are kind of dealing with the effects of cadmium. So it's a serious problem. And so that's the cadmium aspect. And you can also see here the uses on batteries, plating, and also its impacts as well. So it is, so that's cadmium. And then for the chromium, we're going to talk mainly about hexavalent chromium. But in general, chromium is typically used as commonly used to prevent corrosion. And you have three common types of chromium states. Those are chrome metal, trivalent chromium, and also hexavalent chromium. The biggest concern, obviously, is the hexavalent chromium. Going through it quickly, chrome metal is not toxic, but the plating process uses hex chrome, so that is a concern there. For the trivalent, we talked earlier that sometimes, usually you'll see some programs use trivalent with zinc because that's better than trivalent with zinc with hex chrome, but it's still not a perfect solution. The zinc nickel is much better. And furthermore, that trivalent is becoming more strictly regulated, so it will likely not remain a preferred option going forward as well. And then obviously you have the hexavalent chromium. It is found in many corrosion prevention applications. It is very toxic and a carcinogen. It is also highly regulated by EPA and OSHA as well, and Army has been working to eliminate. So here's some testing results, and for this one, we work with the GVSC materials team. Tom Sanders was also one of the award winners, and this kind of talks about where on the top you have zinc with trivalent chromium. So you can see right there, after 1,000 hours of salt spray, you see significant red rust. That's basic, that's corrosion metal. And on the bottom there, you have zinc nickel with trivalent. And for that one, you have double the salt spray, 2,044. And at that time, you're beginning to see some early stages of red rust, but the corrosion performance is superior for the zinc nickel plus trivalent as opposed to the zinc with trivalent. This next slide here is a slide that was given to us by the Air Force, Nate Hughes. He's actually a member of the NASC, which we'll talk about later. But we asked Nate Hughes for permission and he granted it. He also did this presentation actually at the NASC in Utah. So here you can see some testing results. I mean, this picture right here on the right kind of speaks for itself. You have the cadmium plated and the zinc nickel, and you can kind of see the difference in terms of the red rust. And look at how the zinc nickel is holding on very well. The LHE, that stands for low hydrogen embrittlement. And same thing here, you can kind of see for the coating thickness, you can see when you look at 0.5, you can see the LHE for zinc nickel outperforms the LHE for cadmium by about 5,000 salts per hour. So it's just superior. When you look at zinc nickel to cadmium, it's superior as well. So this photo right here, we wanted to kind of highlight, everybody in the DoD often talks about what are you doing for the warfighter? So one powerful quote today that's also going to be powerful 50 years ago, 50 years from now, is actions speak louder than words. So when you look at this, you kind of see how close the soldiers get to exposure of cadmium. An example of this is BAE told us there's a NASM 17829, which they have 144 cadmium-plated nuts that the soldiers kind of deal with, and they're heavily exposed. So this is something that, if we want to be serious about protecting the well-being of the warfighter, this is something that needs to be taken seriously across the entire DoD in moving towards zinc nickel. Okay, so this slide here is some challenges. There have been challenges. One of the first challenges that POGs just told us is there was no single military specification or commercial specification that contained a torque modifier. They defined the zinc nickel plating requirements and the torque modifiers. So the way we address this is with publication of MilPerf 32647. The MilPerf 32647, we'll talk more about that in the next slide, but we added torque modifiers K16 and K20. So for this one, you can kind of see that one of the challenges that we've seen is low volumes. So sometimes we hear from vendors and they'll tell us that is the Army the only one that's adopting zinc nickel? So there's some disconnect there, because when we have correspondence with the NASC and SAE, we have folks from the Navy and the Air Force, NADUs from the Air Force, and also from the Navy, we have NAVC, NAVAIR, and they're all on zinc nickel, but some of the vendors have still not gotten hold of it. So I think we need to do a better job of kind of spreading the word and making sure that all the services kind of get on board with this. All right, so, and then right here, some of the challenges that also, if you're gonna, with the low volumes and also with the no military specification prior to the MilPerf, those two things right there, they kind of correlate with number 3 here. If you do those two things, then the next step is going to be very resource intensive. What that means, you're going to have thousands of new clean part numbers that will need to be provisioned. You will need to have hundreds of drawings that will need to be redlined and updated. And then you would have technical documentation. Like yesterday, we're talking about technical characteristics, and that's kind of part you have to update it. And it's just very time sensitive, and it just takes a lot of time. So GVSC involvement. So as far as GVSC involvement, we crafted MilPerf 32647. We work very closely with subject matter experts from BAE, GDLS, from industry, and also within the military. The MilPerf 32647 added torque modifiers K16 and K20. K16 is the direct replacement for cadmium-plated parts, while K20 was the direct replacement for parts with zinc nickel plating with hexavalent chromium. Those K-factor controls were needed, and it allowed the Army to create threaded parts that can be drop-in replacements for legacy cadmium and zinc-plated parts. Without this, the Army would need to have altered torque tables for the assemblies involved, which would have been an even larger undertaking. And then we also, as
yep. Please be careful about turning away from your lapel.
Okay. All right. And then we also facilitated a review of over 270 military and commercial specs. It was hundreds for both. A lot of them were actually dealt with AIA, NASMs. So we had a lot of MS part numbers that were dirty, and we had to find a clean solution. So a lot of those MS in the 1990s, based on Mr. Sims mentioned earlier this morning, they became NASMs. And now they still have MS part numbers, but they're NASMs. So we had to work with AIA. Chris Carnahan is actually here, and he'll be presenting tomorrow, but we work closely with them. And then we also met with a lot of different committees as well, Standard Development Organization. I mentioned NASC. We also met with a lot of different SAE committees. We got the ACBG, that's the Plane Bearing Committee. We also met with the G3 Committee, the Electrical Connector Committee, which is AE8C1. And then we also have meetings with ASME B18, and that's where there's a pin code system, ASME B18.24, and we got the torque factors K16 and K20 added to that ASME pin code system. Okay, so now about the SIDS. So this is something I know Mr. Hafey inquired about, and I know Chris Carnahan is familiar, but let me just briefly go through this. So earlier today when Mr. Sims was presenting, you guys all saw DoD Manual 4120.24. I think everybody here with standardization is involved, is familiar with 4120.24. So in that manual, there's a provision which says if a non-government standard can be updated or developed in a suitable time frame, then a SID should be developed. So given the urgency of the AAE memo, we kind of pursued the path of having a bunch of SIDs. So we created a total of 17 SIDs here about washers, bolts, nuts, and so on. So when we did this, we heard back from the NASC that they had some concerns about this. They talked about proliferation of part numbers and so forth. So we then had a bunch of meetings. We went through all the SIDs and we said, which ones are threaded and torque critical which one affect threaded and torque critical applications? So we did a review, and the way it's what's gonna happen is the bolt, the nut, and the stud SID, those are gonna remain because those are threaded and torque critical applications. But all the other SIDs from the washer, the clevis, we're working with the NASC. So currently, if you see the clevis, NASM 35A12 had zinc nickel added. So we're currently in the process of canceling AA60031. The key SID will follow soon because there's a ballot currently by the NASC to add zinc nickel to the key. So that one will be deleted as well. So as we go forward, we'll work with the NASC. All these that have planned to cancel, yes. Once we get word from the NASC that those are canceled, we'll begin the process of canceling and with the superseding information. So that's on the SID. And then project benefits. So there's a lot of benefits here. Ultimately, if you look at it, we established close working relationships with industry. We had a bunch of meetings with AIA and also SAE. We've also, the main thing we talked about is the warfighter. Like if zinc nickel proceeds, you're gonna have lower healthcare costs and it's gonna be better for the warfighter and also for personnel that work in plating shops. You can't forget about them. And in general, when you look at zinc nickel plated fasteners, they're just better in terms of they're more economically friendly. They can match the clamping force. They offer better corrosion protection. Their appearance is thin and uniform, and they also have high temperature capabilities. So all in all, it's better for the environment, and it's also better in terms of performance. And lastly, when you look at zinc nickel, this is not exclusive to just ground vehicle systems. This can be applied to the other services. And I know based on our correspondence with the Air Force and Navy at the NASC, I'm encouraged because they're also on board with zinc nickel. So this is something that can benefit DoD as a whole. Okay. And then the next slide, these are all the participants here. So again, GVSC, we're a supportive organization. So we had our spec team and then also our GVSC materials team offer their expertise. But you had Program Executive Office, Ground Combat Systems, and then everybody else that you see here. So this was a team effort, and that's reflected in the participants here on this screen. And then questions.
Alex, I just wanted to say congratulations. I've never seen somebody so passionate about all that.
No, that's my first time. I was kind of worried about the interpreter because nobody's interpreter for me. So I was like, how's that going to go?
I think they gave up halfway through.
They gave up. Yep. You also have to be careful when you're turning. When you're not blessed with gray hair, you know, it kind of exposes that, but you know. Okay.
So can I ask one question?
Okay. Yep.
Regarding the restricted substance regulations, does DoD have a voice in that effort so that, for example, a couple countries have got rid of made nickel illegal in certain applications? How do we get our voice out there?
Well, that's a good question. I think DoD has a voice, and Europe, I think, is more. They're more green. They're even more stricter. But I know on the NASC, we have folks from Airbus. They're from Great Britain, and they're very much worried about passivation and having green stuff. So I think these memos are very helpful. And I mean, the DoD has been trying to get rid of cadmium and hexavalent chromium for a long time, but they're still around. So it's just, you got to get serious about it, you know? So if we're going to be serious about the warfighter, you got to be serious. You know? So, yeah, because right now the major issue we talk about is low volume, and it's like, it goes to the premise of supply and demand. If you have low volume, higher cost. So if you can get that addressed, yep.
So one of the major challenges to defense contractors over the years has been differences in European Union regulations and US REACH, especially in the EU, and their aggressive requirement regarding elimination of hexavalent chrome and cadmium. So it's wonderful to see the DoD stepping up here with the zinc nickel replacement. I commend you for your work with SAE and AIA NASC in this. However, for those of us that also are engaged with FMS, our drive on this is to absolutely standardize on this, that we have all the similar fasteners on the aircraft models that we're either selling domestically or internationally to our allies. Thank you.
And there's some concerns. I mean, right now, I think Chris can talk about it, but I know on FFS 86, we're working to update. And there's always butting heads between manufacturers and, for instance, self-locking companies. It's like when you take a part, you modify it, who's responsible if, God forbid, there's a failure. So it's been hard to get compromised, but we just keep working and try to have dialogue and try to reach a consensus. But there's always issues. Yeah. So, yep. Anything else? All right. All good. All right. All right.
All right, thank you.
Yeah.
And just once again, commend you for the effort working with industry and also with our allies and international partners as well in the development of our standards. So our next speaker, Mr. Rade Sevilla from Naval Air Warfare Center, will be speaking about their project with MIL Standard 1568 materials and processes for corrosion prevention and control in aerospace weapons systems.
So it just stays on, right?
It should just stay on. Yeah, you shouldn't have to press any buttons.
That's not. Can you hear me now? Okay, sorry about that. I'm going to be talking about MIL Standard 1568 materials and processes for corrosion prevention and control in aerospace weapon systems. Here's the basic agenda. I'm going to be talking about the introduction on corrosion, corrosion policy, corrosion prevention and control planning, MIL Standard 1568, and a summary. The DoD the DoD has been fighting a war on corrosion since its inception, and to show that they're serious in combating corrosion, that in the early 2000s they've created a corrosion czar. He's the director of corrosion policy and oversight, and he heads up the corrosion preventative program for the DoD. And also reporting to the corrosion czar, who's the director of corrosion policy and oversight, each service, Army, Navy, and Air Force, has a corrosion prevention and control executive. Why do metals corrode? It takes energy to take oxidized elements into their metallic form. So the metal that is produced is an unstable state and it wants to return to its oxide, which is a metal ore. So the first step in preventing corrosion is to put a coating on. Like for low alloy steels, you put zinc nickel, followed by a passivation, followed by a paint. For aluminum, you would take a passivation or chemical conversion coating, followed by a paint also. A DoD contracted study reported the cost of corrosion to be about $20 billion per year. And that number came up independently. LMI did a study, which came up with that number. Government Accounting Office also came up with a similar number, and the Defense Science Board also came up with a similar number. The corrosion costs are equal to 20% of the maintenance costs. And corrosion is a real problem because it severely impacts readiness and, of course, safety. So it's really important to control corrosion. In the past, too much money was spent on controlling corrosion after it already occurred. And that was called control. It is more cost effective if you plan for corrosion up front rather than trying to fix it after corrosion occurs. And that's the whole idea of corrosion prevention and control planning. On the next slide, if you plan for corrosion up front, maybe you'll increase the acquisition costs up front, like maybe more expensive corrosion coatings, more attention paid to dissimilar material selection so you don't get corrosion from dissimilar materials, more emphasis on training, designing parts with more drainage holes, more ease of maintainability. So when you can access the material surfaces to add corrosion preventive compounds. So higher upfront acquisition costs, you have less maintenance and repair required, lower life cycle costs, higher reliability, higher readiness. So basically, you pay now or even pay more later. On the next slide, I'm going to talk about corrosion policy. And the two main drivers of corrosion policy are Title 10 of United States Code, Section 2228. And that basically instituted the Office of Corrosion Policy and Oversight, which is headed by the corrosion czar. And then beneath him are the 3 corrosion prevention and control executives for each service. Army, Navy, and Air Force has one. And the other important document to take from this slide is DoD Instruction 5060.67. And that document is titled Prevention and Mitigation of Corrosion on DoD Military Equipment and Infrastructure. It's important to realize that MIL Standard 1568 is a Navy AS document, and it's part of a MIL-spec corrosion puzzle. All of these documents that you see here were our Navy AS documents, and they were fully coordinated with both DoD and industry, and they were reviewed by a tri-service team of corrosion matter experts. The first document, MIL Standards 1587, that covers materials and process selection. MIL Standard 7179 is very extensive, and it covers organic coatings and paints and sealants, all the organic materials. On the other hand, MIL Detail 5002, that covers all the metallic coatings and inorganic coatings. And MIL Standard 889, which is a groundbreaking document because it's a game changer. And the NAV Air received the standardization award for that a couple of years back. And the key issue with importance of 889 is it's using corrosion current to determine dissimilar metal corrosion. In the past, dissimilar metal corrosion, how to apply it was based on the corrosion potentials. Like you've all taken like chemistry, and you remember the redox potentials, like copper and gold are positive, and then steel and aluminum are negative. They were basing the material selection based on the corrosion, the potential difference between those metals. Now, the new 889, it forms an experimental way of determining the actual corrosion current between two dissimilar metals. And of course, the last part of the puzzle is MIL Standard 1568, which is what we're talking about today. Now, the next slide. Now, the history of MIL Standards 1568 is very interesting. As you all know, in the 1990s, MIL-STEC reform, which was a subset of acquisition reform, you know, the contractors complained that DoD was too restrictive. We had too many how-to requirements. There weren't enough performance-based requirements. There weren't enough commercial standards being used. There were too many how-to detail requirements. So the Air Force actually converted it to a handbook and said you could not specify it in contracts. It became guidance only, and it existed like that for about a long time. It was this for over 20 years. And what happened was the impetus for bringing it back was the DoD program offices complained that it was too cumbersome to try to take all those requirements and put them back in the contract. They felt it was easier just to have a spec that you could use to cover everything. And so Revision C reinstituted Mill Standard 1568 as a standard. It used to be an Air Force only limited coordination document. And when it was reinstituted as a standard, it became fully coordinated. It didn't really undergo too many technical changes. It was mainly revived to bring it back to life, to make it a requirements document. And it was updated to Mill Standard 962. Then Revision D brought together, again, those tri-service corrosion experts, and they incorporated the latest and greatest industry accepted practices for corrosion prevention and control, and that was released as Revision D. And then Revision E was just published 11 October 2023, and that also updated even more industry accepted practices. But the big takeaway of the Revision E was the new AMP standard for corrosion prevention and control planning. And I'm going to talk more about that later. That's a very pivotal document. It's a very interesting document. And it shows the excellent cooperation between the DoD and the private industry standard groups. What is the purpose of Mill Standard 1568? Well, Mill Standard 1568 facilitates the implementation of a corrosion prevention and control plan throughout the life cycle of the DoD weapon system acquisition. It's something that program managers can actually hang their hat on, because they can put it on a contract and require a corrosion prevention and control plan with deliverables. As I said before, DoD Instruction 5000.67 requires that DoD acquisitions have to address corrosion prevention and control throughout the whole life cycle, from cradle to grave. And Mill Standard 1568 does that by referencing the SSPC CPC 1 NACE document. That's that new standard. I'll talk about more about that later, but that's a new industry standard that was created through a joint effort by DoD, NACE International, and the Society for Protective Coatings. In 2014, the DoD Corrosion Office began working with the Society for Protective Coatings and NACE International to come up with the standard. It's the only document of its kind exclusively developed for corrosion prevention and control planning. So if somebody asks you, well, what's the definition for corrosion prevention and control planning? I would say it describes the specific corrosion prevention and control measures to be implemented for the purpose of maintaining corrosion throughout the entire acquisition and sustainment life cycle. The AMP, I'll just refer to it as the AMP standard, and AMP stands for Association for Materials Performance and Protection. And as I said before, that was created through the merger of the Society for Protective Coatings and NACE International. In fact, I think, it's my personal opinion, that the creation of this corrosion planning and control document, the 21412, I think that was the impetus for actually SSPC and NACE International coming together to form the AMP, Association for Materials Protection and Performance. The 21412 document defines the key elements of what CPC planning encompasses, and it also includes checklists throughout the whole acquisition cycle that are necessary. If someone were to ask me what are the two key components from the implementation of Mill Standards 1568, I mean, not only does it give the lessons learned to avoid corrosion, like it'll tell you, don't put a nickel coating on top of aluminum, because the nickel coating is cathodic, and then the aluminum coating is anodic. So if you get a little break in the surface because of the big difference between the potential, you're going to get a huge extreme corrosion of the aluminum. So that's one of the things that's covered in 1568, the lessons learned, but also mainly the two key components from the implementation of Mill Standard 1568 are the establishment of a corrosion prevention and control plan and a program unique finish specification. Both documents have associated contract deliverable data item descriptions as shown below, the 81402 and the 81403 documents. And as you can see, we talked about the planning checklist and the planning areas on the left there: strategy, design, management, sustainability, supportability, product qualification. And the more detailed checklists are the planning elements, CPC assessment, the finish specification, design considerations, configuration management, maintenance, training, quality assurance program, verification and testing. All those things are part of the corrosion prevention and control program. Now, the finish specification is basically in accordance with Mill Standard 7179 and Mill Detail 5002. And the finish specification, it defines the processing methods, manufacturing techniques, and protective finishes that are going to be used on all the parts in the military equipment. And as you can see, it covers all the different protective finishes, including the cleaning and surface pretreatments, organic coatings, paints, inorganic coatings, electroplated metal coatings, sealants, and corrosion preventative and corrosion preventative compounds. And the nice thing about the finish specification, once it's been approved by the responsible DoD activity, all those requirements have to be incorporated in all applicable drawings and maintenance documents. So just to wrap up, I think the biggest takeaway from revision E was the creation of that AMP standard 21412, and that showed great cooperation between DoD and industry. We did add a section on additive manufacturing in the E revision. We've added Mill Standard 810 for corrosion testing. We've added more material covering nickel alloys, copper alloys, cobalt alloys, and magnesium. Yes, you can use magnesium if you have the proper corrosion protection. And again, it was the latest industry standards, accepted practices were added to the E revision. Okay, the payoff. A Defense Science Board study showed that you could reduce 30% of the DoD corrosion costs through investment in design, sustainment early on in the acquisition cycle. So that $20 billion number that I gave earlier, 30% of that is conservatively $6 billion. I know it's very hard to quantify that number, but there actually was that's just a rough estimate by the a task force that was created by the Defense Science Board a few years ago. So Congress anticipates cost savings because the Director of Corrosion Policy and Oversight has to submit a report or evaluation of corrosion prevention and control to Congress. And they're held accountable, and they have to include analysis of the impact of such potential improvements on system acquisition costs and life cycle sustainment. So each military service, the corrosion prevention and control executive for the Army, for the Navy, and the Air Force, they have to come up with the cost savings and a return on investment and how much money they're spending they have to let Congress know every year what's going on. So I think this standard will be a great tool, an instrument in helping to cut costs. Again, as I said many times before, Mill Standard 1568 was truly a tri-service expert. We received voluminous comments from industry and DOD, and they resolved all the comments and the essential comments. The Mill Standard 1568 draft was coordinated with the Association for Materials Protection, AMP, the Aerospace Industries Association, SAE International. I made sure that it went to various committees under SAE. For example, the Aerospace Materials Engineering Committee and the various SAE commodity committees, such as the Elastomers Committee, the Sealants Committee, the Composites Committee. They all had a chance to comment on the document. And all those individuals shown below, NAVAIR, Navy AS owes a debt of gratitude for their hard work in resolving the comments and help publish a very successful e-revision. So in summary, the use of Mill Standard 1568 will ensure that major weapon system acquisition programs have corrosion control plans. It's going to require Mill Standard 1568E on contracts early on in the acquisition cycle. And it may be beneficial to reassess earlier 1568 solutions due to the issuance of Mill Standard 889. Because when it comes up in maintenance, they may find that some like dissimilar metal bushings, they can actually, if they have to replace a bushing, they can replace it with a bushing that's gonna corrode less based on the new experimental data that they came up with in 889. And that's about it. Thank you very much for your, any questions?
Any questions? Anyone? All right, thank you.
Thank you.
And finally, I'd like to welcome Mr. Rodney Chambers back from DLA Land and Maritime to present on his MILPERF 38535, the general specification for integrated circuits, microcircuits manufacturing.
Okay.
Thank you. All right, my name, you can hear me well. Name is Rodney Chambers. I work with the standardization department and DLA Land and Maritime. And the area I'm responsible for is MILPERF 38535, where I'll be discussing our new rad-hard Class P device, plastic encapsulated microcircuit. I appreciate the award here today and happy to speak here. It's always good to be able to broadcast our information on what we do. And it's also good to hear about what other standardization partners are doing as well to kind of see how it relates and how we help and how we benefit the warfighter overall. This presentation, I wasn't sure exactly how to put it all together, but I wanted to present it in a way today that spent equal amount of time talking about the efforts that we put in coordination and how we work with each other to develop the standard, as well as talk about what we was able to produce here as the new Class P PEM plastic encapsulated microcircuit. So I'll give a little background information about our program and how we specialize in microcircuits, and then I'll go on to talk about our Class P and the requirements and everything that we develop within it. So it sounds, being that this is the Defense Standardization Program, it sounds like everybody's familiar with the DoD instruction of 4120.24. That's the same way the instructions that we design our program around. At the Defense Logistics Agency, our direct department deals with microcircuits and microelectronic devices. Our goal is to deliver high reliable microelectronic devices to DLA supply chain and end user application of U.S. military services and other federal agencies, an example, NASA and allied nations. Again, obviously, we all know what standardization does for each other. And the goal here is to produce more standardized parts of equipment and materials that are interoperable, reliable, and technologically superior. This improves operational readiness, reduce ownership costs, and reduce cycle times for us. At the Defense Logistics Agency here in Columbus that we that operate out of, our standardization division operates and manages over 17,000 standardization documents across 70 federal stock classes and the commodities associated with 275,000 plus national stock numbers. We've been operating for over 50 years now this way, and the spec that I'm responsible for is MilPerf 38535, which is federal stock class 5962 for microcircuit devices. In that program, we are supported by 54 qualified manufacturers with 26 certified fabrications and over 12 plus assembly facilities. And this is supplying over 28,000 plus devices, and 10,000 plus of those are rad-hard devices supported in our program for weapon systems and space satellite missions. We also operate across, we post our documents to the ASSIST website and where we do our formal coordination. And then we also have our own land and maritime website where we post our standard microcircuit drawings. These are drawings that for each qualified manufacturer, it gets listed to 38535. When they produce a device, we create a standard microcircuit drawing based off their manufacturer's data sheet. And we're able to take the critical items off of there, the electrical characteristics, and we put it in the standard microcircuit drawing and we post it on our website. And as a preparing activity, our mission is to provide the warfighter with standardization equipment. And the way we do that is we coordinate with the Army, the Air Force, NASA, and Navy. And also we meet with various suppliers and the user community, and we coordinate that looking at non-government standards out there in industry associations. And we bring everybody to the table. We find out the critical items that's needed from each department, each service, and we try to reach a consensus to produce what we call consensus documents. So we take all this information and we get together and we define what should be the requirements for quality and reliability. And this is how we produce a standardization document. To be more specific in how it relates to our rad-hard Class P now, back around maybe the pandemic time period, we were starting to see an increased demand for commercial call COTS. And we were seeing a lot of our committees that we're associated with and working groups that we participate in. We were seeing a lot more conversation geared around what they were labeling as alternate grade parts. And just trying to figure out ways of using commercial plastics, commercial parts, and upscreening those to whatever their mission standards would be. So being that was becoming a more dominant conversation, we decided to create an EP study around that time. EP study is an engineering practice study where we looked at, some of these committees got together and produced an upscreening, what we call an upscreening document, and it was SAE AS 6294. There was a -1 and a -2. So in our engineering practice study, we tried to look across what other manufacturers' enhanced product flows were. We looked at these new upscreening documents. We looked at the automotive spec of Q100 and tried to do a comparison of what we can do in MilPerf 38535 for our screening and QCI testing against what people would perform for upscreening to try to qualify these devices. The outcome of that was when we looked at trying to produce that, we found out that there was more of a demand for space rad-hard plastic parts and not necessarily the military application. So there were a lot of users coming to those manufacturers looking for a space market part. And all these manufacturers had their defined enhanced product flows. So getting together to try to produce a standard to get them to build to would obviously be more beneficial for that manufacturer and also the user. And that defines, at least you have a certain level of understanding of what it was already designed into that part. So I want to put this slide together to kind of show, I think as a standardization body, I think everybody has how they work with industry and how they coordinate and how they gather feedback and market research and everything else that we do. So in our specific area, here are just some of the branches that we work with in different departments. NEPAG, you can see, is the NASA Electronic Parts Assurance Group. And with them, we have weekly teleconferences where we get together and we talk about some of the concerns with microcircuits and everything. So how all these different organizations work here is when we created that EP study, I was able to present this information at each one of these bodies. There's a lot of cross-reference between the participants in these working groups. And let's say like NASA Electronic Parts Packaging Group, that NEP, they produced a lot of articles where they did a lot of research to define what each manufacturer's enhanced product flows were. And they were showing comparison between each manufacturer. Now, each one had their own certain testing and standards that they would do to it. So I was able to look at some of those documents. I was able to get with NASA, and that's how we did a comparison flow in our engineering practice study. We also would share that information across what we have as a government working group, which we meet bi-weekly with, that we discuss these items of anything of critical nature. And in those groups, we have the Army, Navy, Air Force, and NASA, who we prepare our documents with. And again, like I said, there's multiple cross-body organizations here. Many people that participate in some of these organizations, they're in a lot of these meetings as well. And these are bi-weekly and weekly teleconferences that we have. And one of the important pieces that we go to is called the JEDIC Council. And in there, they have a specific group for JC13, which is made up of your manufacturers. And it even further defines JC13-2, which is a body that we have triannual conferences with, that we all get together over maybe 100 to 300 participants and liaisons from manufacturers and the users and the primes. And we discuss what's important for our MilPerf 3535. So I was able to present our engineering practice study there and kind of gather more information and feedback of what's needed and what the manufacturers are willing to do as far as testing and screening for their product, and then discuss that with what the users really want and need, and make sure you don't over-define the spec and try to get that coordination. So within JEDIC, we actually defined a working task group that began to meet bi-weekly that had great participation from the community. We had a manufacturer from that body lead, that one of the leading manufacturers for some of our plastic parts. And then we had one of the users that co-chaired that committee, and we would meet bi-weekly to kind of define what the screening and what the quality conformance testing should be in that spec. Go to the next slide. So again, through numerous meetings and telephone conferences and emails, and even developing small working groups from who you would consider the subject matter experts from each of these organizations, we got together and kind of ironed out what the manufacturers are willing to do for this new standard, and then what the users would agree to. So we're trying to create that consensus. And it was around March of 2022 that working task group finalized their proposal for us to present to formal coordination that we would do on the ASSIST website of our MilPerf 3535. And like I said, it was a multi-year effort, and we were able to coordinate all that. And once we presented it, based off of the kind of work that the different exposure that we did in engineering practice study, presented that information at various working committees, it actually kind of made that process a lot more streamlined and faster when we put it into the document for coordination, where our 45-day review that we only had minimal feedback from, and we was able to answer all those questions based off of that kind of coordination. Just to go into a little bit more detail about the requirements that we established in our new Rad-Hard Class P. Within that working group, we looked at it from a screening standpoint, where we do 100% screening on our document, on our processes and then the devices. So just highlighted here are some of the items that created a lot of discussion in those working groups. And like being able to have those working groups, you get a lot of feedback from the manufacturers and the users in those meetings. to try to meet a consensus. And I know one of the big things at that time was, would they do acoustic microscopy on every part for 100% screening? And we couldn't get the manufacturers to necessarily agree to that. And the users were okay with that, as long as we, in our parts and our what we call Group B testing for our test tables, we have a package-related qualification test. As long as we included some form of acoustic microscopy there, so they can look into the device and look at delamination or any other issues there. And that's done on, it's not 100%, but it's done on a periodic standard. And another thing that we were able to agree on was our, what we call Group E testing, which is our rad-hard assurance testing that we already have in MilPerf 38-535. And they kept it as similar to what we already produced for what we call Class V, which is our ceramic grade hermetic devices for space level. Again, when we create the standard now, instead of it being more of an upscreening document, we have qualification of characterization and design, technology, characterization, everything that goes into it now, where we have a qualification table that we get to see all these processes and ask questions and look at their quality management plan and ask more questions. And so we get a lot more feedback on how we can advance our spec in the future. I just wanted to put an example here of, here's one of the test tables. This is our Group D test table. I just wanted to put this up as an example to show we have our hermetic classes of Class Q and Class V, and then we recently produced our non-hermetic classes, which are, you see, is Class Y, Class N, and Class P. Class N would be your military grade device for plastic encapsulated microcircuits, and then Class P is more of our space grade. And I just wanted to itemize it individually to show when qualifying to one of these standards, you can actually see if you're producing whichever class it is, you can kind of go down that test table and do these and perform these tests as needed. As I mentioned earlier, for each one of our manufacturers that qualify to our new Class P, you would have to produce a device, and on these devices, we create a standard microcircuit drawing. So each standard microcircuit drawing, as I mentioned earlier, we have our electric, it looks similar to the manufacturer's data sheet, but on there, we actually, it's a standardized form. So you know where to look for each item in a standardized format. You're looking for the information, you can, it's understood by everybody and they know what they're looking for. And one of those sections is our rad-hard features section, which is 1.5 in our SMDs. And there you will see items listed as far as the total ionizing dose levels that they are able to achieve, as well as the heavy ion single event effects that were tested and reviewed by them. You would definitely have to acknowledge that, you know, this is something being new, going to be continuous development, that there's going to be some challenges that we come across as we create a standard for this. And in doing so, qualifying the first few manufacturers, you can start to see that many of the tests that they're being used and test methods that they're using to qualify their parts is more of a commercial aspect, because we use MIL standard 883, which is our test methods for microcircuits. And that test method was mainly designed around ceramic and hermetic devices. So now we've come into a standpoint where we're looking at a lot of non-government standards that are being used. And you can't diminish the effect of what they have, because they have a lot of input in them, but you got to keep in mind that a lot of these non-government standards that were designed around commercial activity, maybe automotive, and that's who has the larger voice in those rooms, versus our military standards where we have our application-specific missions involved. So we want to maybe develop some more working groups to define the need for where should we start adopting some of these non-government standards, and where should we look at some of these non-government standards and start updating our MIL standards, because some of our MIL standards need to be a little bit further defined for the mission applications that we're going to be using these devices in. And then just at the bottom of the slide, I had a few examples of some of those tests that people are using some of the non-government standards out there. And what we're doing in the meantime, we list our military standard as a requirement. And as long as that's listed as a requirement, that manufacturer has to meet that requirement. And if they can't, if they use something different, our qualifying activity will review what they're doing, how they're performing it, and they will have to review that for whatever justification on how they can prove that they meet the standard that we're looking for. Some of the benefits, as we know, when it comes to standardization that this Class P is produced for us, obviously this will help eliminate the use of non-standard devices, which contain pure tin and different device lead finishes that can promote tin whiskers. We have our requirements in there that these are designed around our military and space grade, high reliable applications. So again, we've seen studies in different articles, and even some of our meetings, NASA has said how much cost savings that this has provided for them by having a standard and kind of getting the communities to start pushing this standard versus all those other upscreening documents and having the manufacturer do special things. But then when they get the part, they still have to do upscreening. And then you end up finding out that even upscreening a device can end up being more expensive than just purchasing the qualified product itself. A standardization document, it now has, it helps define the article that we're buying. And then, you know, it's not non-standard parts. They have a lack of, just the commercial items might have a lack of engineering, technical characterization and reliability studies done on them. And obviously some of the commercial items will go obsolete a lot more sooner, where we actually push for these devices, if you're qualifying on that they have a longer life cycle. Again, more benefits as far as more of your commercial grade parts. More of your commercial grade parts don't necessarily meet the temperature ranges that we're looking for our applications. And our military grade spec is going from -55 to 125 C. As I mentioned, longer life cycles. And then just some of our current users we included here. Now, every time we create a standard microcircuit drawing, we ask that, who are you designing this for? So we making sure that this is for our users that we want these to be for, and our military, our warfighter. So some of those users are MDA, NASA, L3 Harris, and you can see more of them listed on that bottom bullet. Just another example to show how this is creating standardization. So we had a manufacturer who already had a ceramic grade device, and it was listed on what we call our SMDs. And then they came back and added the Class P device for plastic encapsulated microcircuit, and it's rad hard as well. And typical rad hard levels that we're seeing is total ionizing dose levels of 50 to 100 K rad. And I just wanted to point out here on this slide that you can see by this standardization, you have it on the same drawing, and you have two different devices that meet a certain level of reliability, obviously. And you can see that the size difference between the Class V part, which is your space grade part, and then the plastic Class P part is about half the size, double the power density by being half the size, and then look at the weight reduction that it'll do for you. So, as far as the status update on our Class P right now, we finished to finalize the spec in 2023, and already we have 8 Class P documents approved, with 15 more already in process. Our active sources right now is Texas Instrument. They're the main ones. We're getting new devices. It almost feels like on a monthly basis proposal that we're working on them in process. And then some of the other manufacturers, I heard from our quality side that we're working with some of these manufacturers now. Some of them showing interest, and some of them are actually in current process of being qualified manufacturers. And as far as the outcome and cost avoidance that we're looking at, we estimated this based off of SD19 and some of the other documents. This is a 2013 estimate that we looked at, and it's about, they said the cost of adding a new part to a system was roughly around $27,500. And so we look at this, if we can produce 125 non-standard parts each year for the next 5 years, we're looking at a cost avoidance of $3.43 million annually, up to $17.15 million for 5 years. And it's always kind of hard to try to get these estimates and put them together, but we definitely do see, once we produce these devices, a manufacturer will look at it, user will look at it SMD, and they're not just purchasing one device, they're purchasing maybe 5 of these for their application. So if we can get more of these devices in that have this higher reliability, that's less changing and longer life cycles that these parts provide. So the last slide here is the path forward is what we're looking at as far as in our department, and some of the things that we're doing just to kind of advance our standards with technology. we had many ongoing working groups working at the same time where we were looking at the use of lead-free within the microcircuits. And we restricted that to the use of just flip chip devices internal to the device. And we've had working groups that define mitigation techniques. So we've been able to adopt that. We were able to adopt plastics into the spec now, updated our military grade plastics as well as our space grade plastics. And the main thing that we're working on now is this is creating a lot of conversation. It is our greater than 2D technology. Greater than 2D technology as your system and packages, and this is your latest technology. And we don't currently have a lot of the tests that define what this is. So we've got a working group now defining how to rad hard these parts and these stack die within these microcircuits and everything, and how they communicate, how to test them. So that's we're taking what we learned and producing these standards so far, and then that's the next thing that we're working on, how to advance that, and what we're calling advanced technology microcircuits. And that concludes my presentation for today. Again, I thank you for the time. Thank you for the time to present this. And it's always good to be able to share this information of what we're doing with different organization bodies, because it seems like we all do some portion of it, something different. And it's always good to be able to hear what other people are doing, how they're doing their experiences. So definitely appreciate the time to share. And are there any questions?
I got one.
Yes.
So you mentioned lead-free solder and you mentioned tin whiskers. So that's the issue with lead-free solder in high reliability electronics is tin whiskers.
Right.
So with this plastic encapsulation, do you get rid or reduce the need to have solder?
So with our Class P parts, we've actually had a lot of discussion around that, and a lot of them are using gold wire bonds on their die. A lot of the dies are being fabricated with aluminum pads on it, and our ceramic Class V part, we like to have a monometallic bond. So we have aluminum to aluminum, which you can avoid Kirkendall voiding, tin whiskers, and everything like that. Internal to the part, we're using gold wires to these aluminum pads. And these are wire bonded. So there's no pure tin at all allowed in these parts. And as far as lead free, some of them are considered lead free, I want to say, but they have their mitigation techniques involved with them that there's no fear of tin whiskers or anything like that. So.
All right, thanks.
Yeah. Yeah.
Was that 27,000 roughly per part? Was that only for kind of like these standardized parts? Like that's not ASICs or anything like that, right?
So that was just looking at the document. That was the estimate that they gave. I've actually visited an Air Force base recently where I actually just asked them what's the general cost of what it takes to redesign based off of a new part, and they told me numbers around 40,000. So we went off that 2013 estimate, and that was 27,500. And I understand that would just be if you have a fighter jet and you have to redesign around a new device being put in there. I'm guessing that's the overall cost of what it would take. Is that what you're asking? I'm sorry. Yeah. All right.
Just one more quick question.
Yeah.
So there's been commercial satellites. Are you seeing, and the standards that you're using and developing, they're based on non-government standards to some extent, and you coordinated with industry. Is it too early to say, are you seeing any trends to where there is a commercial interest in some of these standards based on the interest in like commercial space travel and some of the activities there?
I guess that's so when we first did the EP study, you were hearing this discussion come up a lot around alternate grade parts. How can they start using alternate grade parts? And they're looking at these for mission applications that aren't as critical. So that's where it began and that's where it started. Some of these parts, we know that they are flying, but that's probably after they did a lot of their upscreening. And our goal was to establish our QML standard. And if we can hurry up to establish that QML standard, that would eliminate the use of each one of these manufacturers producing their individual flows for their commercial grade. And if we can put our footprint there, then maybe their design techniques and their flow techniques would be more geared towards qualified parts versus the commercial parts. And we have different programs for commercial grade parts. We have a bid program that we operate, where we work with our manufacturers that we are familiar with, and it's baseline around our QML program, but it's their commercial parts. So they use a lot of the techniques and characterizations that they would use one fab site, one assembly site, one test site. They don't use countries that we're not friendly with. So we have a lot of these things that we kind of work with, and we still hear a lot of people wanting to use commercial parts, obviously. Our goal is to use more QML devices. So that's what we try to push and focus on the most. And if we can establish something that's usable within that sector, then hopefully we can gear more parts in our QML products. All right. Thank you.